Functions show up in a variety of different contexts. In particular, they show up often in physics. Now, in this lecture, we're going to look at one-dimensional particle motion. Before I begin, I should say that the entire theory of calculus was really developed simultaneously with modern-day physics. So the advent of classical Newtonian mechanics with calculus really occurred simultaneously. Calculus was invented to do physics and to describe problems in physics. And it was a very powerful tool in which we can describe that thing. And over the centuries, we found that this mathematical framework describes a diversity of other complex situations in biology, engineering, just the list goes on and on. Biology, engineering, ecology. There's examples everywhere. Airplane dynamics, metallurgy, structural mechanics, fluid mechanics. They sound like a lot of physics-related courses, but a lot of different fields: business, modeling revenues and costs, and so forth. The basic and the most simple example of classical mechanics is just a particle traveling along a one-dimensional line. So you can attach whatever story you want to this. That's not very straight. That's better. So we have a one-dimensional line, which we'll call the x-axis. And basically we have a little particle traveling back and forth, moving about. So this can take a variety of different contexts. It could be a man walking back and forth along a sidewalk, or a woman walking back and forth along a sidewalk. It could be a stone being tossed into the air and coming down. In this case, the axis along which it's traveling is a vertical axis. So x of t, or x, would represent the stone's height as it went up and then it came back down. It could be an ant walking back and forth. It could be distance between your home and a store, and a car traveling, a car on the highway. Lots of different stories you can append to this, but basically it's just a particle that has a one-dimensional range of motion. It can go to the left or to the right, where left and right don't necessarily mean left and right. They could mean up and down, but basically one way, the other way. That's one dimension. It can just travel along a line. It can't move in a plane. It can't move in three-dimensional space, just along a line. So functions show up here because we model a function, x of t. So this is the particle's position as a function of time. What is a particle? Well, the idea of a particle is it's a concept in physics. Sometimes it's referred to as a point mass, meaning just a point that has mass to it. We're not considering the mass at the moment, just a particle. So the particle might be a woman walking to the grocery store. It could be a bear running to a lake. I'm not sure if bears run to the lake, but it could be ants marching along a celery stick or something like that. So it's just saying whatever. It could be the stone moving through the air, going up and then down. So it's just a particle is just a generic term for whatever it is that's moving back and forth. Okay, so we'll just call it a particle. So x of t measures the particle's position as a function of time. V of t gives the particle's velocity as a function of time, and then a of t represents the particle's acceleration as a function of time. So very often used system of units, x will have units of meters, right? So m, and then t units of seconds. So s. So then of course v has units of meters per second, and acceleration has something called units of meters per second squared. Now, what's a meter per second squared? It seems a little bit strange. And the idea is it's meters per second per second. So you can say meters per second times second, or meters per second squared. So in other words, if you're accelerating at 5 meters per second squared, it means that every second, approximately 5 meters per second is being added to the existing velocity. So it's basically your velocity is increasing by 5 meters per second every second. Different units, miles per hour per second would be something similar. Like 20 miles per hour per second means that every second your velocity is increasing by 20 miles per hour. That's roughly around 1 g. A g, so 1 g, you've heard about g-force. 1 g represents either 9.8 meters per second squared or 32 feet per second squared. So these are equivalent. And what a g represents is acceleration due to gravity. And you might say, well, what's acceleration due to gravity? Well, if I take a pen, ironically, this is an anti-gravity space pen. This is the AG-7 that was used in the Apollo missions. Not the actual pen, but it's the same model. So it writes upside down, but it's ironic that it's an anti-gravity pen because I'm about to drop it and watch it fall. So a little bit of irony. So here's my anti-gravity pen, which doesn't mean that it will float when I let go of it. It means that it writes upside down. But when I let go of it, notice it doesn't stay still. Right? So it has zero velocity. As soon as I let go of it, it suddenly picks up a downward velocity. Right? You've seen things drop before like that. Yikes. Okay. So no velocity, and as soon as I let go, it has velocity, and the velocity increases. So if I drop this from a 10-story building, it will be going faster and faster and faster until it hits the ground, right? So it's actually accelerating. The velocity is not constant. It just keeps in a linear rate. It keeps picking up velocity, and that's what acceleration due to gravity is. So we've measured this, and it's 9.8 meters per second squared, or in English units, 32 feet per second squared. So that's acceleration due to gravity. So we have position, velocity, acceleration. Now these three quantities have a very intimate relationship, which we'll explore in greater detail later on in chapter 2. So when we introduce derivatives, we'll see, even though we don't know what a derivative is now, but the velocity is a derivative of a position. The acceleration is the derivative of the velocity. We'll find out what that means later. But for now, we can just think of the position, velocity, acceleration. So those are the three main things that we quantify when we look at particle motion. Essentially, the velocity tells us the rate at which the position is changing. It's so many meters each second. If you're walking 5 meters per second, that means each second you cover 5 meters of space. Acceleration is a measure of the rate of change of the velocity. If you have an acceleration of 5 meters per second squared, that means the velocity is not constant. Every second, 5 meters per second is being added to the velocity at a linear rate. So let's say we can graph. Let me change the color here. Here's t and here's x. So if we were to graph this, it would look something like this. Maybe we do something just simple like that. So what this represents, so here's my axis. There's the x-axis. Now, and here's x is equal to 0. So I'm starting a little bit with a small positive position. I go up, go down, and I come back. So that's what this graph would look like in time, right? So I start here, x is increasing to a maximum, starts increasing, it passes through 0, or it starts decreasing, passes through 0, decreasing, stops, and it comes up. So this tells you your position as a function of time. So I start here, move up, go down there, come back. Right? So in time, so here's the actual axis. In time, the motion is starting here, going up, coming down, going back. Just like this goes up, down, back. Except here the x-axis is vertical, so you kind of have to look at it sideways, and here it's laid out. But it's small positive, increasing, decreasing, increasing, and just does that sort of thing. It's here, like that. So you kind of have to, it's kind of just, you practice a little bit, you get used to this. You know, looking at a graph like this, you can say, okay, you know, on this interval of time for the first 1 second, the position goes from here to there, then the position goes from here, passes through the origin, goes down there, then it comes back up. So that's kind of how a function like this might look. Now, now let's say the x-axis is vertical, and this is the ground. So let's say x represents the height above the ground. Height above the ground. Okay. So you toss a ball up. So sometimes an object that's been you know, thrown through the air is called a projectile. So we have a projectile that was launched with an initial upward velocity, and a little while later it's here with a shorter velocity, then it's here with a small velocity, then it reaches the top, and then it goes down, then it's here with a little velocity, here with a bigger velocity, and then it hits the ground with a big velocity. So the ball goes up, and then it comes down. So it's like that, straight up, straight down. If we plot this with respect to time, something like this. So here's time, and here's height. So as it turns out that when you toss an object straight up, it goes up, it comes back down. There's a formula for this. So x of t, and it turns out that if you plot the position of an object like this, that you toss up in the air, you see it go up, stop, it come back down. It doesn't like stay stopped, it just, at one moment it's stopped, because at the moment it stops going up and starts going down, it has 0 velocity and it comes down. As it turns out, the position as a function of time is actually quadratic. So we have a formula, x sub 0 plus v sub 0, or v naught t, plus 1/2 a t squared. Now the question is, what do all of these parameters mean? So we have the parameter x sub 0, v sub 0, and a. So x sub 0 is the particle's initial position. In the case of motion under gravity, it would be height. Actually, I should say this is even more general than just one-dimensional motion under gravity. It's any case in which you have constant acceleration. So these are the equations for constant acceleration. Gravity accelerates objects at a constant rate, so in that case, x would represent the height above the ground, and you get the same equations. But it's anything with constant acceleration. If you're on a roller coaster and you're ready to take off, and you go from 0 to 60 in 3 seconds, constant acceleration, you just take off, and there you go. This would describe your position as a function of time. X sub 0 is your initial position, v sub 0 is your initial velocity, and a represents the acceleration, and it's the constant amount. So it has to be constant. You can't, if acceleration is a function of t, you can't replace a for that function of t in this formula. This formula won't work. It's only if the acceleration is just a constant. And then the velocity as a function of t is equal to v0 plus a times t. Now this rather makes sense because basically acceleration tells you how your velocity is changing. So if your velocity is changing at 5 meters per second squared, it's just your initial velocity, and then plus every second I'm going to add 5 meters per second onto the initial velocity. So if my initial velocity is 0, it's just 5 times t. So after 1 second, my velocity is 5. After 2 seconds, my velocity is 10. After 2.5 seconds, my velocity is 12.5. After 5 seconds, my velocity is 25. Every second, exactly 5 meters per second is added to the velocity. And then a of t is just the constant a. So these are the equations for constant acceleration of a particle moving along a one-dimensional line. Now, velocity and acceleration and position can be positive or they can be negative. It makes sense the position can be negative because it depends on how you define your axis. If you say this is the x-axis, here's the origin, and then the particle's free to move wherever it wants, negative position just means it's over here instead of over there. It's intuitive enough. Negative velocity is different. Velocity is positive when the position is increasing, and it's negative when the position is decreasing. So if you're moving to the right in this example, you have a positive velocity because something's being added to your position, so the velocity is positive. If you're moving to the left, you have a negative velocity. So it's subtracting from your position. Instead of being at position 5, you're now at position 3, now you're at position 1, now you're at position -1, and so forth. So the sign on the velocity tells you which way you're moving. So with this projectile example, so I launch a cannonball straight into the air. So basically it just goes straight up and comes back down. If you plot that as a function of time, you see a parabola up and then down. It goes up and comes back down. So the velocity is positive because it's so you're adding to the height. Positive velocity, positive velocity, positive velocity, positive velocity. Zero velocity at the top, negative velocity, negative velocity, negative velocity, negative velocity. So positions increasing, velocity is positive. Positions decreasing, velocity is negative. Increasing, decreasing, velocity positive, negative. And then acceleration too. Positive acceleration means you're adding to the velocity. So it's an upward. You're getting, if you're moving to the left, you're going to start moving to the left slower and slower. You're not going to be moving it to the left as fast, as quickly. So like say if you're moving 20 meters per second to the left, your velocity is -20. And let's say my acceleration is 5 meters per second squared. Every second I'm adding 5 meters per second onto the velocity. So if I start off with a velocity of -20, 1 second later my velocity is -15. It's still going to the left, but not as quickly. 2 seconds after the start, my velocity is -10. 3 seconds later, -5. 4 seconds after the start, the velocity is 0. I've stopped moving to the left. 5 seconds after the start, my velocity is 5. Now I'm moving to the right. So you see what happens is that if acceleration is positive, it tends to push the motion to the positive x direction. So it tends to push the velocity towards the positive x direction. If the velocity is negative, it will slow it down, stop it, then start moving it to the other direction. Negative acceleration moves it in the other direction. So up here, acceleration, we'll call it -g. So g was our 9.8 meters per second squared, so the acceleration is -g. Because it's a downward motion. The velocity starts off positive and then it ends up negative, so the velocity is decreasing. So acceleration due to the gravity should be negative because it's acting in the negative x direction, because by the way I define my x-axis, the x-axis is pointing upward and the gravity goes down, so it's a -g. So these are the main equations of motion. Let's work out a simple example with this. Let's do this. Let's say I'm standing on a 50-meter cliff. Oh, not a 50-meter cliff. I don't have a tape measure with me, so I don't know how high the cliff is. I'm just standing up here. There's like some nice beach ocean view, everything's nice, as long as the cliff doesn't like slide off. And I want to figure out how far it is to the ground. I have two things. I have a stopwatch and I have a rock. Well, I picked up the rock from the ground, but I can get a rock by just picking one up. They're everywhere, and I have a stopwatch. And I'm going to use those two things alone to figure out how high I am off of the ground. So the idea is I take my rock, and I hold it out, get my stopwatch ready, drop the rock as soon as I start my stopwatch, watch the rock fall, and then as soon as it lands, hit my stopwatch. I find out how long it takes to fall. 6 seconds. Say it's exactly 6 seconds to fall. I actually visited a castle in Germany. I was an exchange student in high school, and it was kind of on this like mountain, and then there was like this sea, and the castle was up here, and they had a well, so they had to get to sea level, so they drilled this well all the way down to sea level. Actually, some of prisoners, they didn't drill it. There were no drills in the Middle Ages. They dug a well down to sea level. 2 prisoners, the story goes, dug the well in exchange for their freedom. It took them 10 years to dig this well, and then they were freed when they came out. Of course, the well was covered with a screen so nobody falls in, but it was really cool because they poured some water down the well, and you heard, let me get the timing right. So you basically heard right? So it took about 6 or 7 seconds for the water to reach the bottom. How high were we? How far off of sea level would that be? So that's the question we're asking here. We measure how long it takes for something to fall, and we can figure out how high we are off the ground. But we don't know our height. Well, first of all, let's do coordinates. X, we always want to assign variables. X measures the distance above sea level. So X is the height. So it's basically the distance above sea level. Because sea level is down at the ground here. Or the distance above the ground. Okay, so x of t is equal to x sub 0 plus v sub 0 t minus 1/2 g t squared, where g is equal to 9.8 meters per second squared. Negative because downward gravitational acceleration. Now we need to figure out before we do anything what the initial height is. Well, x sub 0 is your initial height. That's the problem, because how do we do anything with this equation if we don't know x sub 0? V sub 0, we need to know the initial velocity. Now this rock that I drop, I just hold it and then let go. So it starts with 0 velocity. So the initial velocity is 0 meters per second. So that simplifies things. X of t is equal to x sub 0 minus 1/2 gt squared. Now what about x sub 0? I don't know what the initial height is. So let's assign a parameter to that. So let's call this h. Let's say the cliff has height h. So h is it's a constant. A parameter is like a variable, except you treat it as a constant. It's just an unknown constant. So t is the variable because this is a function of time, and the position is varying with time. A parameter is basically an unknown constant. So you use a symbol to represent some unknown constant, but you treat it like a number. You don't treat it like a variable. You treat it like, well, maybe the height is 100 meters, and that's just what it is. It's going to be 100 meters. It's just a constant that we don't know what the constant is, so we use a. So let's introduce this parameter h. So x of t is now h minus 9.8 over 2 is 4.9 t squared. So this will tell us the height of, x, the height of the particle as a function of the number of seconds since I dropped it. Now, how do we use this to figure out what h it represents, or what the value of h is? Well, I just say, well, what do we know? We know that it hits the ground at 6 seconds. So when it hits the ground, we're at t is equal to 6. So therefore, x of 6 must equal 0, because when the rock lands on the ground, it has 0 height. So when t is equal to 6, x of 6 has to equal 0. X of 6 is 0, so after 6 seconds, the rock lands. Well, now we just have h minus 4.9 times 36 is equal to 0. So h is equal to 4.9 times 36, 176.4. So if it takes 6 seconds for the water to drop to the bottom of the well is approximately 176 meters deep. Pretty deep well. So then of course you can, starting with this initial equation, you can, do whatever variation you'd like on that. So, you could be given the actual initial height and say, well, how long does it take to land, right? So then you set it equal to 0 and solve for t, right? So here we were solving for the height, the initial height. So we used a parameter to represent the initial height, set this equal to 0 and solve for the initial height. Maybe we know the initial height, but we don't know how long it takes to land. Well, now we know h, and we set this equal to 0 and we solve it for t. So let's say if it's 200 meters tall, we would have 200 minus 4.9 t squared is equal to 0. So 200 divided by 4.9, 195.1, because mentally I say, okay, this minus this equals 0, that means this must equal this. Now let's divide both sides by 4.9, so 200 over 4.9 is equal to t squared. So t squared is equal to 200 over 4.9. See, that mental math helps. Square root, and that just improves with practice. So t is 13.96. Now that is quite odd. So always you want to keep in the back of your mind the idea of doing a reality check. Does this make sense? So if the height's 180 meters, it only takes 16 seconds to fall. But if the height's 200 meters, it takes almost 14 seconds to fall. Something's not right there. Let me see if I did the calculation right. 200 divided by 4.9, square root, sure enough. Oh, that's not 13.96. I don't know what button I pressed to get that or what mistake I made, but something was not right with that number. 200 divided by 4.9 is 40.816. Square root 6.3887. So time is 6.3887 ... So it's approximately. So about 6.4 seconds. An extra 4/10 of a second if your height was 200 instead of 180. Now let me go back to that reality check, how I knew 13 seconds couldn't have been. First of all, the rock gets faster and faster as it falls. So if I'm at a height of 180 meters versus a height of 200 meters, if they're dropped at the same time, this first rock dropped at a height of 180 will reach the ground when this second rock has reached a height of 20. So it takes the same amount of time for both of these to fall their first 180 meters. So basically, we're only looking at a difference in traveling an extra 20 meters. Now it's going to be going pretty fast at this point, so it shouldn't be very long. It shouldn't be that it takes 7 seconds to fall 180 meters, or 6 seconds to fall 180 meters, and then an extra 8 seconds to fall those remaining 20 meters. That makes no sense whatsoever. So I knew I made a mistake, because I'm like, well, that's if the first answer was 6 seconds, this is way too long at 14 seconds to just fall an extra 20 meters. Right? So always ask yourself when you come up with an answer, does my answer make sense? Does this make sense with everything else I know? Does it make sense with my intuition, with physical experience? Because oftentimes that can tip you off into knowing that you made a mistake in your calculation. I gave a problem once for a Calculus 2 class, and this was group homework, so these were groups of 4, and it was basically, you had a table with the fuel economy in miles per gallon of a truck as a function of its velocity, and it traveled from like this velocity to that velocity over a 30-minute period of time. And the fuel economies were like 20 miles per gallon to 30 miles per gallon, somewhere in there. Maybe even 15 miles per gallon, but something like that. Two of the teams came up with an answer of like 1,200 gallons of gas used in a half an hour period. Those teams did not do the reality check. They should say, wait a second, 1,200 gallons in a half an hour? I mean, how often are you filling up here? I mean, it's just not, it doesn't make any sense. There was a unit issue where they didn't convert units right somewhere when they set up this sum to do this approximation. But I love that story because it's just such a blatantly obvious that 1,200 gallons of gas in a half-hour period has to be wrong. It just has to be, right? And you can even go back and look at the numbers. So the worst case scenario was, this speed, because this speed has, or the worst gas mileage is 15 miles per gallon. The fastest speed is 50 miles per hour. So then you can work out, well, if I take the worst gas mileage and do the fastest speed so that I travel as, way more than the distance I actually traveled, how much gas would I have spent? And it's like, it works out to be like a gallon or something like that. Well, you can work out the details. So worst case scenario, you're spending 1 gallon, 2 gallons, whatever that calculation works out as, not 1,200 gallons. So those reality checks really are important to do and to keep in mind. So that caught my mistake right here. Whatever I typed into the calculator, I pressed the wrong button or something. I guess it's hard to talk and punch stuff in the calculator at the same time. So that's how you do these sorts of physics problems. And of course, the velocity is your initial velocity plus acceleration times time. So if it's downward acceleration due to gravity, it's v naught minus g times t. And you can answer questions like, always think, what information are you given? What information are you trying to get? So when this is equal to 0, it's at the top of the trajectory when it comes down, because positive velocity is going up, stops with the 0 velocity for its instant, and then it starts coming down with a negative velocity. So if you want to know, how long, so if you launch something from ground level, shoot it up, stops, comes back down, and you know the velocity, how long did it take? Well, you can set the velocity equal to 0, and that tells you how long it took to get to the top of the trajectory. Multiply that by 2 to get the time of the full trajectory. So you set the velocity equal to 0, solve for t, and you can figure out like how long it took to go from ground to the top of its trajectory. And then by symmetry, it should take the same amount of time to go from the top of the trajectory back to the ground. So, there's a plethora of different ways of asking questions with these basic equations, but always it's just those 3 equations, and then write down what you know. Use a parameter if there's some constant that you don't know, and then interpret like what information you're given into an equation, and then solve for your unknown. So it's always that sort of procedure.